morning, everyone. Thank you all for attending and logging on. We'll just give other attendees a couple more minutes before we get started. So we'll aim to get started before 5 minutes past 10. Okay, so we have a good number of attendees now, so I think we'll get started. So thank you all for registering and logging on for CurrENT's webinar From Risk to Reward, Why Innovation at the Distribution Level Can't Wait. My name is Ewan Ramsey, Policy and Communications Officer at CurrENT Europe, and I'll be moderating today's event for what promises to be an insightful discussion. Europe's electricity grids have rightly been in the spotlight as a key enabler of European competitiveness, and today we will be examining how risk, as well as perceived risk, has been limiting the deployment of innovative grid technologies which can help unleash the full potential of Europe's electricity grids, both in the near term and in the future. The agenda for today's event is as follows. I will be presenting an outlook for DSOs. Mark Norton from Smart Wires and chair of CurrENT's DSO working group will be presenting the second edition of CurrENT's recommendations for the deployment of DSO projects. Rina Kuwahara, energy analyst in power system transformation at the International Energy System Agency, will be discussing the pace of grid development. Eftima Kasati and Konstantinos Kermidis from IPTO will be presenting a case study deploying Smart Wire's modular power flow control. Alberto Mendez, CEO of PlexiGrid, will be discussing the importance of digitalization at the distribution level. And Ricardo Valati, chair of the infrastructure workstream at SEER and team leader at ARERA, will be discussing regulatory regimes that can help support the deployment of innovative grid technologies. Lastly, we will finish with a Q&A session with the audience. Before we get started, I would like to go over some housekeeping rules. In order to remain on schedule, I would ask that all questions during the speaker's presentation be asked with the chat function. This will enable speakers to respond directly in the chat over the course of the webinar. We have allocated 30 minutes for interactive Q&A with the speakers at the end of the webinar, where you can raise your hand using the chat function on Teams and ask a question that has potentially more nuances or is more in depth. If a question is unable to be answered due to time constraints, CurrENT will either answer these questions directly or reach out to the speakers for the answers. We will then upload these answers online as well as the recording of the webinar. So without further ado, we'll get started. Next slide, please, Paul. So as mentioned, I'll be presenting an outlook for DSOs. Next slide, please, Paul. It's undeniable that this Commission's mandate has been shaped by the need for a strong, resilient, and reliable electricity grid. The now infamous Draghi report set the scene for how Europe needs to evolve in order to remain competitive in a changing geopolitical environment with the competing powers of China and the United States. In the report, high and volatile energy prices were identified as key barriers to European competitiveness. In 2023, industrial electricity gas prices were 158% higher than in the US, squeezing already tight budgets and reducing the capacity of European industry to expand. We saw the spike in energy prices in 2022, driven largely by the impact of restrictions on Russian gas imports. The impact of these volatile price increases on consumers put into the spotlight the need for European energy autonomy driven by electrification. To facilitate the dual goals identified by the European Commission of decarbonisation and competitiveness, stronger electricity grids with increased levels of renewable energy sources integration have been identified as a key enabler. The European Commission has laid out a clear pathway through the publication of, amongst others, the Competitiveness Compass, the Clean Industrial Deal, and the Affordable Energy Action Plan, all of which provide steps to facilitate the major upgrades required of Europe's electricity grids. Next slide, please, Paul. DSOs will need to play an increasingly important role to incorporate the increase in RES that is coming on now and are projected to become available in the future. By 2030, it is estimated that around 80% of the renewable capacity will be connected at the distribution grid. What is clear is that in order to achieve these goals, large-scale investment in the distribution grid is needed. As the graph on the right-hand side shows, the level of investments into the electricity network have steadily grown since 2015 and are projected to continue to grow. Of the nearly 100 billion of annual investment needed, nearly 2 out of every 3 euros must be targeted towards the distribution level. This is further emphasized by the European Commission's communication and EU action plan, stating that the investment needs at the distribution level to be around 375 to 425 billion until 2030. This amounts to an increase of 50 to 70% of investment in the 2020 decade compared to the previous decade. The question must be asked about what happens if we fail to achieve these levels of investment. Aside from not reaching Europe's electrification targets, the cost of energy that can ultimately be passed on to consumers are enormous. In Germany alone, roughly 50% of the 9 terawatt hours of curtailment were connected at the distribution level. This amounts to around 800 billion worth of curtailment per year at the distribution level, with this figure likely to rise if the pace of renewable project deployment and development outstrips necessary reinforcement and upgrading of the electricity grid. The scale of this problem is clear. How then can innovative grid technologies alleviate this issue? Next slide, please, Paul. Published in June of last year, CurrENT partnered with Compass Lexicon to release a study investigating the impact of the deployment of 8 different innovative grid technologies and the benefits they could bring to the grid. This included a 20 to 40% increase in overall network capacity and a 35% reduction in conventional expansion costs, equating up to 700 billion up to 2040. A key insight was the scale at which grid build-out must be expanded at the distribution level by between 20 to 65%, equating to around 13 million kilometers of distribution grids by 2040. To achieve this, the required build needs to increase 3 times in scale, working on 250,000 kilometers of distribution grids per year. When comparing capacity requirements achieved using line length equivalent, targets could be achieved 4 to 7 years earlier at the distribution level, thanks to the optimization of the grid through innovative grid technologies, meaning the cost and electrification benefits of a more optimized energy grid can be capitalized upon earlier. Next slide, please, Paul. So, to summarize the points made here, it is clear that the distribution grid is essential to achieving Europe's competitiveness targets and has been identified as a key enabler of these ambitions. The European Commission has clearly set out its legislative agenda and targets. Close to 2/3 of grid investment will need to go to the distribution grid, making it a priority. Curtailment will rise with a lack of investment and potentially cost consumers billions annually. Innovative grid technologies must be deployed as part of these solutions. I will now hand the floor over to Mark Norton, Vice Chair of CurrENT and Chair of CurrENT's DSO Working Group, where he will present the updates to CurrENT's latest edition of recommendations for the deployment of DSO projects.
Thanks, Ewan. Maybe we can just move on to the next slide, if you don't mind. Thanks, Paul. So I've just got two things to talk about today, and I'm going to try and do it in, well, certainly less than 20 minutes. That has been allowed for me to give us a bit of time back. The first one is just to briefly introduce the DSO deployment paper and the updated recommendations. I'll do that very quickly, and then really to provide the opening consideration for this webinar. We're looking at moving from a risk to a reward situation in regards to innovative grid technologies, and why the innovation that will result from that at the distribution level can't wait. And I'll sort of set the scene, I suppose, and expect a number of the other panel speakers to follow. Okay, so maybe we'll get the first slide. So just to talk a little bit about the DSO deployment paper and its the update, but probably the first thing to do is to say, well, why does it exist? And there's three key factors, I suppose, behind the DSO deployment papers. Being a living, breathing document, one that's updated on a regular basis, this being the second edition. And that's the recognition that DSOs have significant resource commitment and restriction. The scale of the challenge, we've heard Ewan talk about it previously, is huge. It's growing. There's a significant need to both renew and develop and extend the distribution network. The role is changing rapidly, and as a consequence, time is precious. Resources are few. There's a lot of work to be done, and we're trying in this deployment paper to make life simpler, to find a single source of reference for a number of different technologies, their pros and cons, how to look at them and evaluate them, work with them, to help with that resource commitment issue. Justifying technology number two is very, very difficult as well. Innovation is rapid, it's very fast, it's uncontrolled to some extent, and certainly moves much more rapidly than the existing standards can keep up. And we're finding that, obviously with the range of technologies that are coming through, increasing exponentially, it's extremely difficult to envisage that the time and energy can be put into those standards to actually keep them in line with the innovation as it develops. But we know that DSOs, unlike their transmission cousins, have had to, from the sheer scope of the number of projects they're doing, place a high reliance on standards. So that is a big issue to manage, and we try in the paper to talk about what standards are available, how you can use the ones that are available to look at some of these new technologies, and how to manage it when you don't have them available. Managing uncertainty is one that we'll talk about the rest of the presentation really on. We see that innovation is key. Everybody says it, whether it be the European Commission at the political level, policy and direction, whether it be with the regulators, and ACER and SEER, and obviously the national regulators as well. Everyone is singing the fact that innovation is absolutely required. The system operators certainly are, connecting pilots and so on. But it's making it very much more difficult to justify innovative projects. They are more difficult. They are new. They're a new concept for people to get around. Sometimes the costing is difficult. The paper tries to address this as well. So that's the three factors. Can we move on? Thanks. Thanks, Paul. So the paper, just at a helicopter view, we have the 5 existing technologies we have in there, from advanced conductors to monitoring sensors. They have all been updated and refreshed. New references, new information, new examples have all been added. But we have 2 new technologies, partly at the request of this audience and a similar webinar, 12 months ago, looking at what new technologies need to be examined on the distribution system. And as a consequence, we now have high temperature superconducting cable systems that have been added to the brochure, as well as innovative software solutions for grid optimization. It is, as I mentioned, a live document, so we will continue to add in new technologies as they arise, and obviously it's drawing on the expertise of the membership of the association as well. Maybe I can have the next slide, please, Paul. Along with the update to the document as a whole and the new technologies I mentioned being added, we have also updated our recommendations. Some recommendations, quite gratifyingly, have been moved forward apace and have sort of entered into policy and are perhaps moving to a different phase rather than calling for them being delivered. But there are new things that are coming on stream and new issues that need to be tackled. The new recommendations we have are a mixture of some of those old and new. So efficiency first. We would be great advocates of making the most of the existing network. Innovative grid technologies obviously do that. Not surprising them that we are strong advocates, but talking a little bit about some of the challenges that are involved in that and the reasons. And you've seen some numbers that the UN have provided, looking at the scale of the benefit that could actually be provided. You know, we're talking about hundreds of billions in savings potentially over the next 10 to 15 years. A focused distribution technopedia. We're very happy to see that a technopedia is in development between NSOE and the EU DSO entity, and so that's great. But we do see that there does need to be a focus on distribution technologies within that. So whilst it's great that there's a singular document with one voice, we do realize that there needs to be a focus put on the differentials between transmission and distribution. Some distribution technologies in the Technopedia won't apply to transmission. Others will need to have a distinct differential between the two. And it's absolutely critical that we don't just have a Technopedia in name, but it is actually used. So we would expect that all the technologies that are listed in the Technopedia will be actually considered in each national reinforcement development strategy and plan for each of their individual projects, and ideally will be noted as having been considered and the reasons why they've been rejected in favor of whatever the solution is for that particular project. Not only are we looking at just the individual technologies themselves, but we've been calling now more and more, and people are starting to understand the technologies, the symbiosis, the ability to multitask with these technologies and to combine them is a real driving power. You can get multiples of the benefits by combining them. Innovation incentives. We were really gratified with the Copenhagen Infrastructure Forum and the European Commission and ACE's push towards benefit sharing and other innovation incentives that are similar in nature that will make the introduction of new innovation and to reward that justifiably to the system operators for making that shift. That is a key cornerstone for making the kind of change that we need in the innovation to come onto the system. The last two, we're going to talk a little bit more detail in the next slide. So minimizing technical assurance. We understand that there needs to be an understanding of the technology and an investigation, but often it's replicated where we're not using the same learning, and trialing what matters. So at the end of the day, you want to fulfill a role. We can look at 1,001 things, but when you're looking at innovation, the thing that you should be trialing, the thing that we should be sticking on, the growth and is managing risks that are real, and those risks need to be proportionate as well. And I'll talk about those in the next 2 or 3 slides, so I won't dwell on those now. Can I have the next slide, please, Paul? Okay, so let's just talk a little bit about, and I mentioned, trialing what matters. I mentioned risk and the focus. At present, I think it's fair to say that the concern, the appraisal of risk is very much focused on the technology or the innovation that you're putting in itself. So when you're going through an investment decision and you're trying to look at a new technology being added to the system, and this would be similar in transmission as in distribution, there's a different approach, and we talk about that in the paper. It tends to be a one-off assessment done at distribution, a sort of type test, and then that decision is made to how it will be replicated on a number of the projects, less bespoke, but the same underlying focus is there, which is really looking at what's the risk to the project of using a new technology. And one of the common determinants or that are used in that, and you'll see it in the technopedias, is the technology readiness level. It's a common measure that's used. Most people would have heard of TRL, but the calculation method used is not universal. It varies from company to country, country to country, and certainly, at a European level, it would be different to what would be done, say, in the US. And as a consequence, they can be quite difficult to benchmark. But using one of the known sources, of course, being ENSOE's Technopedia, and some of these are drawn from this. It doesn't reflect directly to distribution, but as we've got to wait until the end of the year for that combined Technopedia, I'm using this to help for the purposes of this discussion. We can see that TRL 9 commercial readiness, i.e. that the highest level that you can get into TRL, the one that says, yes, this should be fit for purpose, is not an automatic guarantee that they will be that technology will be used and enter into a widespread use or become an industry standard. If we look at some of the existing technologies, overhead lines clearly are considered to be the industry standard. Cables maybe a little less so. Both of those would be at TRL 9 or above. But then a number of the innovative grid technologies, although considered extremely mature, so modular power flow control, DLR, or advanced conductors, would be at TRL 9. Some of the others would be lower down towards TRL 6. Are not being put into widespread use. So even having achieved a high readiness level, they're not being applied. But still, some other technologies that may be at lower levels are more in widespread use. So it seemed that even when you're looking at appraising it from a risk perspective, the readiness, but it's not universally applied in the same way. However, when we look at a project risk and a technological risk, what we're missing is a completely secondary factor, which is probably more dominant and important. Can I have the next slide, please, Paul? And what's that? Well, I'm talking about system risk. So what we see is the fact that, yes, there is a risk of installing a technology, or perceived risk, and it is a perception, we would say. But then there's the actual risk to the system as a whole. And that's often missed when we're looking at a project by project level. And those system risks are growing. One of the reasons that people are calling for innovation so strenuously is for the key contributors to system risk. So they're getting missed at a project by project level, and yet they still exist at the system level. And that's the economic cost. When we look at all the projects combined, the spend is enormous. When we look at the timeliness of the solutions, a vast number of the projects, and you can go to a number of different reports to look at this. The IEA have published timelines. We've had ACE's monitoring report looking at the deliverability of some of the projects that are actually coming through. Individual development plans, the project of common interests often report as well. So there's a number of things at a European level as well as at a national level that can be examined. But the delivery of solutions is becoming delayed and extended, and it's obviously making a hot topic. But also very much growing as well is the recognition of flexibility in services that are required on the system. If we actually combine these and try and look at the same technological choices and say how they would plot when we're looking at system risk as opposed to project by project risk, we get a completely different story. In that, we can see that the innovative grid technologies score extremely highly. They're fast, they're cheap, they generally come with a large number of added capabilities as well. So they become very low from a system risk point of view. Often they're smaller in nature, so they're incremental. And we can see a number of sources at the bottom here that show, both the timelines, some of the costs that are associated with this, the overall net savings, the stepped increase of putting in smaller solutions, and the overall time that can be saved on a large portfolio, a number of projects. I've shown some sources here. There are a number of other ones you can draw on. They're very common in their findings. And Therefore, if we look at system risk as opposed to project by project, we can see the fact that innovative grid technologies can really help manage that overall system risk much more effectively than conventional solutions that make up the majority of the plan at the moment. But at the moment, these are missing. Very rarely are they looked at on a project by project level. So can I have the next slide, Paul? So let's combine the two of those together. And if we look at a number of risk and reward assessment tools, they would all profess the fact that you need to look at the likelihood of an event happening and the scale of the impact. And a lot of those that are being used in a widespread fashion look at the impact not just on a project level, but they would actually advocate that we should be looking at it on a system level. So we've got the UK Network Asset Risk Assessment, NARM, as an example, being used obviously at the UK, NERC, so across the US of A. We've got the severity risk indicators. They would both be very heavy on that. In Europe, and looking across the whole of Europe, we have the Winter Adequacy Outlook by NSOE. It's not obviously trying to measure the risk to system performance from network reinforcements, but the principles outlines and the concerns and the risk method that's in there looks at exactly the same thing. What's the likelihood of having insufficient generation, and what's the scale of the impact, and trying to measure those two things. There's a consistency on what people are doing. And yet when we look at a project by project level, this is not actually occurring. If we look at that and we take into account that security of supply system risk is required in decision making. I mean, at the end of the day, the principal requirement or mandate is for security supply on the network. And we also take into account that innovative grid technologies are much lower in risk. If we look at the table at the right here, we can see in the top right-hand corner technologies in the form of DC cable technologies and the VSC converters, and to some extent the hybrid overhead lines. I'm showing the cable specifically just for simplicity, but they all fit in that sort of TRL 6 to 7. Their risk to the system is extremely high, but also their perceived risk from a project level and by their own scoring, by the industry, would say that they're very high, and yet they make up 50% of the plan. So we've obviously been able to justify on a project by project basis or system wide the use of technologies that fit into that category, that present both a higher technological risk because of their TRL level and also their impact on the system. It would seem obvious that innovative grid technologies that may have a higher perception of risk should be used much more extensively than they are at the moment. And if we consider that the risk, and through this evaluation and the discussion that will follow, that there's a misperception and there's a miscalculation by looking at it on a project per project basis and not at a system level, then we should look and say, well, what are the rewards of actually taking a more brave, if you like, approach, or a more measured approach maybe to risk, and balancing it a little bit more with the system risk in order to get the evaluation better and more improved. Well, we see some of the rewards at the bottom. The ability of innovative grid technologies, and some things have been touched on already by Ewan, are huge. If we look at the distribution system, so just breaking the distribution system out, there's about 350 billion euros worth of spend that could be saved up to 2040. We could see a 60% growth in grid costs over the same period to consumers. So clearly, if we can provide that same kind of benefits using newer technology on each individual project, we could significantly reduce that, particularly as 75% of that expected growth to consumers is to come from new build. We can also look at the risk of delivering the projects and the entire portfolio. Everyone is of the has every stakeholder in the industry has been very strong in professing the fact that a failure to deliver these projects on time has huge risks for the economy, the health, the stability, and the longevity of the European system and its economy. Being able to deliver that portfolio much earlier de-risks all of those things and provides much greater benefit as well. From calculations, innovative grid technology could provide a 4 to 7 year acceleration of the portfolio of projects. And finally, we've got the ability measured to go a 500 gigawatt growth in capacity flexibility that's required over the next 25 years. So, flexibility on the system, as I said, is growing. 500 gigawatts is an enormous growth requirement, and over a 25-year period, having reinforcements that can provide inherently a lot of this flexibility is also something that provides a significant reward in its own right. So I'm going to stop there. There's some ideas and thoughts, and I'm sure that next speakers will pick up on some of those, maybe in their presentations, but certainly in the panel session at the end. And thank you for listening, and thank you for your time.
Thanks very much for that, Mark. And yeah, so just to the attendees, I'd like to remind you, if you do have any questions over the course of these presentations prior to the Q&A session, please use the chat function to participate. So now I'd like to introduce Rina Kuwawada. Rina has been working in the electric power sector for 20 years, dedicated to renewables integration into power grids and markets. From assessing wind and gas power compliance and transmission losses in Australia to testing the robustness of European power grid planning and operation, her career has spanned continents and from technical to policy levels. Now, since joining the IEA last year, she's been leading the agency's work on power grids and regional interconnection for decarbonization and enhancing energy security. Rina, the floor is yours.
Thank you very much, Ewan. Thank you to CurrENT as well for this opportunity to speak today about this critical topic for our energy transition, accelerating the deployment of technologies that will enable more secure and efficient grids. As Ewan said, my name is Rina Kuwawada. I'm an energy analyst for power system transformation at the International Energy Agency. Today, I'll examine 3 key aspects of grid technology deployment. First, the urgent need for accelerated grid deployment and the consequences of if we fail to act. And then second, the specific challenges in distribution grids and digitalization, including the constraints and risks we face. And finally, regulatory innovations that can support deployment, concluding with actionable priorities for moving forward. What you might find missing from my presentation is a description of each of the technologies, and that's a little bit intentional because it was largely already given, and many of the peers today will go into more detail on that. So without further ado, I'll start by emphasizing that the scale of grid development that's needed is really immense. The age of electricity, where heating, cooling, and transportation are expected to become electric, as well as industrial processes and public infrastructure, the power system needs to transform. And in our report, Electricity Grids and Secure Energy Transitions, that was published in 2023, we found this, what you see. Over the next 2 decades, we need to add or replace 80 million kilometers of grid infrastructure, equivalent to the entire global grid length today. And this calls for grid investment to double from today's level by 2030, keeping pace with investment in renewable energy and its expansion. So the urgency cannot be overstated. Grids are super important. The European Union recognizes this as well, and investment rose, as was shown earlier as well in Ewan's presentation, from 80 billion, it rose to 80 billion euros from around 50 billion euros in previous years, supported by the Commission's Grid Action Plan, which targets 600 billion over the next 6 years. However, the challenge remains in sustaining this growth and overcoming things like supply chain issues, especially for power transformers facing inflation and shortages. Next slide, please. So our report that I mentioned on electricity grids, it also looked into what could happen if the grid development fails to accelerate at the pace that it's needed. Our analysis of a grid delay case showed that renewable projects would remain stuck in grid connection queues, while would also fail to leverage critical flexibility sources like demand response. And this would keep wind and solar's global electricity share nearly 15% points lower longer term. And instead of major fossil fuel reductions, coal cuts would be halved and natural gas use would actually increase from today's levels. So fuel importing countries would face extra costs up to $500 billion US. Naturally, CO2 emissions would then be affected too. This would be 60 billion tons higher over the period to 2050. And this creates a 40% chance of exceeding 2 degrees Celsius warming by the year 2100 versus the 1.7 degrees Celsius of commitments, if the commitments are met. So grid delays could also increase costly outages that already cost the global economy today around $100 billion US annually. Next slide, please. Distribution grids require urgent attention in this story. By 2030, distributed solar capacity will more than double, outpacing utility-scale PV growth, and the number of electric vehicles will increase fivefold. This transformation drives major investment needs in infrastructure that has historically received less attention than transmission. A major portion of this needs to go into distribution. And integrating these millions of new connection points requires both the physical grid reinforcement, but also increased digitalization. Digital tools enable the essential coordination between transmission and distribution systems while facilitating flexible resources at the local level to manage bidirectional power flows. Next slide, please. Digitalization needs to expand, and luckily it has been. Digital technologies have grown from 12% of total grid investment in 2016 to 20% in 2022. 3/4 of this went into distribution grids. But deployment could be faster. Traditional cost of service regulation creates problems here. This model, where utilities recover cost plus a return, favors capital over operating expenditure, and it doesn't effectively promote digital solutions. The European Commission recognizes this challenge as well, and their digitalization action plan allocates almost 30% of grid investments to digitalization by 2030. Next slide, please. As we pursue deployment of grid technologies, we face significant constraints and emerging risks that must be addressed head-on. High investment needs coincide with compressed timelines. Supply chain bottlenecks extend lead times for critical equipment. Also, the workforce is challenged, and this is equally pressing matter. Utilities are competing globally for digital talent. You can see there on the left chart. Our analysis shows that European utilities are falling a little bit behind other regions in recruiting digital talent. This is creating a critical gap in implementation capabilities as well. On the right side, we see an emerging risk, which is cybersecurity. Here, electricity-related cyber incidents have increased over the last decade. With greater digitalization, this creates new potential vulnerabilities. So we need digital expertise in both regulators and utilities to enable better risk management and create this effective deployment incentives for grid modernization. Next slide, please. These deployment delays affect more than just emission targets. They could also impact European competitiveness and increase system costs. It was already mentioned about congestion management costs. Here are some figures on the left. These have more than tripled in recent years in countries like Germany, Great Britain, and the US. The Netherlands is not shown here, but it also has similar levels of increase. And this is due to lack of grid capacity. Quick deployment of grid enhancing technologies can help alleviate this pressure by optimizing existing infrastructure while new lines are also being built. On the other hand, on the right side here, we show some statistics about innovation and patents. And here, global innovation leadership is starting to shift. Europe used to lead grid technology development from 2009 to 2013. However, in 2022, China has surpassed the EU in grid-related patents, especially in smart grid technologies. So strategic deployment of these technologies, innovative grid technologies, it serves multiple goals. It helps meet emission targets, strengthens energy security, and maintains Europe's competitive position in the global clean energy landscape. Next slide, please. We can go to the next one. Thanks. Here, regulatory innovation is really key for accelerated deployment of the innovative grid technologies. Some examples that we've picked up in a couple of our recent reports. One of them that I want to highlight is regulatory sandboxes. Maybe you are familiar with this term. It emerged in the UK and the Netherlands in 2015, the concept, and is now being adopted quite commonly across the globe. And these frameworks provide temporary exemptions from certain rules to safely test new solutions before they are widely implemented. For some recent examples from Europe, in 2024, Denmark launched its first regulatory test zone for integrating high shares of variable renewables at an industrial cluster. And in Spain, they introduced a sandbox on voltage control with incentives for large consumers to absorb excess reactive power and prevent voltage surges. And it's not shown here, but you can also access from the web. Maybe somebody already mentioned it. There's a paper from ASA and Florida School of Regulation on benefit sharing. And in this paper, it highlights benefit sharing mechanisms that reward utilities for finding innovative solutions by giving them a portion of the cost savings compared to the traditional approaches, creating a win-win for both utilities and consumers. So these are great examples of innovative regulation and new ways to move forward, because well-designed regulatory testing environments combined with benefit sharing mechanisms create pathways to bring new innovative grid technologies to market more quickly while protecting consumer interests. Next slide, please. So as we work to accelerate its deployment, a few takeaways to move forward. First, planning. We must prioritize the modernization and efficient utilization of existing grid infrastructure alongside the new development. And strategic deployment of grid technologies is essential to maintain European competitiveness in global innovation. Second, unlock investment. We need to appropriately incentivize investment in grid modernization and new technologies. Regulation should reward utilities for adopting innovative solutions that increase system efficiency. Third, address barriers. Reform regulations to encourage adoption and scaling of smart grid technologies. Create frameworks with targeted incentives that help utilities manage implementation risks effectively while moving from pilots to mass deployment. Fourth, leverage digitalization. Use demand-side flexibility and distributed resources to optimize existing grid capacity and reduce the need for extensive upgrades. And finally, build a skilled workforce. We must foster digital skills across all domains. Create a talent pool with both digital and electricity expertise. The challenges are significant, but the cost of delays are greater. With coordinated action across these 5 areas, we can realize the full benefit of a modernized and digital grid.
Brilliant, Rina. Thank you very much. So we will now move on to our next speakers. So we have 2 speakers from IPTO. We have Eftima Kostasi and Kostasinas Karmidos. Eftima received a degree in electrical engineering from Aristotle University of Thessaloniki. She also holds a PhD in management science from Lancaster University. She's been working for independent power transmission operator SA since 2007 and is currently Head of Section Technology in the Department of Research, Technology and Development. Her research focuses on applying innovative technology in transmission system infrastructure and in control centers. Konstantinos receives the diploma and PhD degrees in electrical and computer engineering from the University of Patras in Greece. He is currently working as a researcher with Research, Technology and Development Department in Ipto, Greece. His research interests include smart grids, renewable energy sources, grid enhancing technologies, and their integration into the system operations. Eftima and Konstantinos will be presenting a case study deploying smart wires, advanced power flow control. The floor is yours.
Good morning, everybody. So the purpose of our presentation is to show how IPTO handled the deployment of a new technology, the MPFC. So it would be an interesting use case. Also in the transmission system operation level, it would be interesting how an operator handles the deployment of a new technology. Next slide, please. First, let's describe how this device operates. So what this device actually does, it injects voltage into the line that is shifted by 90 degrees with a current. So depending if it is leading or lagging the voltage, we have inductive or a capacitive operation. If we divide the injected voltage by the current line, then we have the effective reactance. This can be positive or negative, depending if you have inductive or capacitive operation. So this is how it operates, and the purpose is to affect the power flows. We all know that the power flow on the line depends, of course, on the voltages on both ends, but also on the total reactance of the line. So if we have this MPFC, we can add or subtract the effective reactance of the line. So for example, if we have inductive operation, we have positive reactance, so the total reactance increases and the power flow decreases. In the other case, we can have capacitive reactance, so it's negative. So the total reactance of the line reduces, and so the power flow increases. On the left figure, we can see the different values of the injected voltage that the MPFC injected according to different values of the current line. And if we divide the voltage by the current, we get the effective reactance, the two envelopes we can see in the right figure. So we can see here that the reactance takes positive and negative values, as well as the voltage can take positive and negative values. Next slide, please. So here we can see the MPFC that was deployed in the Greek transmission system. With one is labeled the base steel that ensures the support of the complete design. Labeled with two in the figure, we can see the post insulators that ensure we have the safety clearance we need. With three, we have the smart valve devices. This is the device that injects the voltage. We can see we have two of them. This structure can have up to 5 smart valves per phase. So this is a proof of the modularity and the scalability of this device. 4 is the smart bypass. So this bypasses the smart valve. So it's like we don't have anymore the MPFC, doesn't affect the transmission line. And with 5, we have the bypass filter that makes sure that high frequency signals do not enter the MPFC. Next slide, please. In order to control the MPFC, we have to communicate. So here we can see the communication scheme of the MPFC. In the Greek transmission system demonstration, The MPFC communicated with radio signals with the power line coordinator. This is a device that is installed nearby in the substation. And then the power line coordinator is connected via Ethernet with the power line gateway. The gateway then provides different opportunity for communication. In the Greek demo, in order to keep it simple, we used a GSM operation, meaning a simple SIM card, which was connected with a computer that had the smart interface, the software that controls the MPFC. Of course, there are also other possibilities, for example, to integrate in the communication system of the TSO, and then, for example, send it to the dispatch center. Next slide, please. Also, there is a flexibility in the control methods. This is the monitoring, where we have bypassed the MPFC, so it doesn't affect the transmission line. We have the fixed reactance, so the voltage injection changes accordingly to the line in order to have a specific reactance we have determined by the operator. We have the fixed voltage, meaning a specific voltage is injected, also again determined from the operator. And we have also the current control. In this case, the MPFC starts injected when the current exceeds a specific threshold. Next slide, please. So we saw how it operates, how it affects the power flows. And let's see a very generic use case. For example, we have three lines, parallel lines we can see on the upper figure, with one of the lines being overloaded while the other two are underutilized. Here we can exploit the MPFC with different ways. One possibility is to install the MPFC in the overloaded line, choose for inductive operation, and then push, let's say, the power to the other two underutilized lines. So in this case, we resolve the congestion. Another option would be to install the MPFC in the underutilized line, activate the capacitive operation. So power now is pulled to this underutilized line. And as we can see again, the congestion is resolved. So this is a generic use case. Next slide, please. So I'll pass now the presentation to Mrs. Caciotti.
In order to observe the impact of the MPFC device on the interconnection line between Greece and Bulgaria, the Nea Santa substation, located in the northeast part of Greece, was selected. As seen in this line diagram on the slide, in this area, there are many wind parks. Load flow studies helped identifying the most restricted lines due to their limited line capacity that could constrain the amount of power which flows through the transmission grid before it becomes overloaded. One of these lines was the Nea Santa Iasmos line, and this was selected. This is a 150 kV line, and the decision was to place the MPFC inside the Nea Santa substation, which had sufficient installation space with no social acceptance issues. Next slide, please. The construction and the implementation of projects that are connected to the electricity transmission system of Greece have to conform with certain requirements depending on the voltage level and also on the operating condition as specified in the tender invitation if the project is outsourced, on static and seismic safety requirements and the respective national and international laws and regulations. For research programs, internal cooperation with all involved IPTOS departments is needed. Next slide, please. Yes, so about the installation now. what we did is that we actually had the previous support structure designed by Smart Wires for a 330 kV use case in Australia. And this was now used because IPTO approved the use of this design for a 150 kV network, taking into account the different climatic and seismic requirements. The differing standards, notably in steel quality and contents, were also considered and approved. The weights and loadings of the structure were used in designing the ground foundation and in adjusting the overhead line configuration. Indeed, the fact that the MPFC was installed in the context of a pilot project expedited the approval process. Next slide, please. Kostas, you can continue.
Yes, thank you. So describing a bit the details of the installation, we can say there are two main phases. It's the preparation phase and the second phase, which is the actual installation of the smart valves. Next slide, please. So the first thing we did was to build this concrete basis upon the complete device would be installed. This took around 25 days, which included also the time that the concrete needs to cure. So in above we can see before, and in the figure below we can see when the concrete bases were finished. Next slide, please. Also, some adjustments were done on the overhead lines. First, in order to ensure we have the safety clearances. So the first adjustment was to move a conductor and a line, the middle face of the transmission line, to the right. So you can see, if one observes the figure with the tower, we can see that we moved the middle face from the left side to the right side. Also, some adjustments were done in the conductor inside the substation, so we can see that the right face were moved a bit to the right. And finally, we, let's say, broke the line. We put some insulators in order, we can see in below right figure, in order in the second state to have the ability to connect the MPFC in series with the transmission line. So this took around 2 days, this whole work for adjustment of the overhead lines. Next slide, please. Then we proceeded to the actual installation of the device, which took 9 days of work and 3 days of outage. On the figure up left, we can see where the top frame is installed. On the figure up right, we can see the first commissioning phase, where we powered the line with a generator and a load bank. So we make sure that everything works properly and we have any problem. And in the figure below, we can see the actually finished implementation of the MPFC, where now it has been connected in series to the transmission line. Next slide, please. So before implementing this technology, we did a lot of simulations using the model that Smart Wires had provided. I won't go to many details because of the limited time, but we examined different use cases. For example, we had increase in the load, increase on the rest production, different power flows with Bulgaria, the connection with Bulgaria, N-1 scenarios. And average impact, what we saw, it was we could redirect the power flow from this line to other power lines in the order of 5 to 10 megawatts. Next slide, please. So here again, we can see the different simulation results. Next slide, please. And here are the results for the actual testing of the device. We tested all the control methods. So also voltage injection and reactant injection we can see in this slide. And and we observed that the impact was in the order we saw also the simulation results, so around 5 to 10 megawatts. So this means the simulation and the actual demonstrator were in good agreement. Next slide, please. Here again, we tested the current control mode. So we saw here when the threshold was exceeded that we had determined, the MPFC successfully was activated and started injecting voltage to the line. We also wanted to see what was maybe the biggest impact we could have. So we transitioned from inductive to capacitive operation. And we saw a big impact of 100 amperes, this equivalence to 25 megawatts, that was redirecting from this line where the MPFC installed to other power lines. Next slide, please. I pass again the presentation to Ms. Cassiotti.
Concerning the risk management of the project, as we have already mentioned, there is need to comply with requirements for turnkey projects in IPTO, while minor deviations from these requirements were assessed from IPTO with additional studies. Also, installation in the context of the pilot project and experience with an older version of SmartWire's MPFC device facilitated internal procedures. In addition, certain characteristics of the MPFC device, for example, its internal bypass functionality, help to considerably reduce operational risks. Last but not least, the key role in risk management is the support for the vendor. And in our case, there was excellent cooperation with SmartWires, who were always willing to answer any questions, provide on-site support, and cooperate with IPTO. Next slide, please. What we see as benefits from this technology is that in certain cases, it can be an alternative way compared to lengthy reinforcement projects. Indeed, license procedures sometimes can be lengthy. In these cases, it can potentially help to faster connect renewable energy, reducing network congestion and increasing system reliability, as well as reducing the environmental impact of transmission investments. In addition, the MPFC device can help in managing outages for maintenance reasons and also could be used as a bridge solution for resolving overloads. Indeed, after the FARCROSS project, IPTO assessed the use of this technology to deal with a congestion issue that is foreseen to occur in another part of the transmission grid. Next slide, please. In conclusion, the power flow controller technology advantages were verified during the demonstration, starting from the fast delivery and installation, the ability to redeploy, the modularity, the scalability, the reliability, and the flexibility in control modes. The simulation and real-time results were found in good agreement. Through the FARCROSS project, IPTO had the opportunity to participate in pilot demonstration of state-of-the-art innovative grid technologies like the modular power flow controller and become familiar with a promising technology for dealing with congestion issues in the future or in other areas of the transmission grid and generally the network. Next slide, please. Thank you for your attention.
Thank you both for that great presentation on the in-depth, the overview of MPFC and how it can be deployed in real time. I'd just like to remind all attendees that if you do have any questions during the course of these presentations, please use the chat function, or please feel free to use the chat function to ask questions directly to the speakers. And this is in addition to the 30 minutes of allocated Q&A session we have at the end. Now, the next presentation we have is from Alberto Mendez. Alberto is an executive, investor, and entrepreneur dedicated to the energy transition. He's held leadership roles at Siemens Gamesa, Vattenfall, XCharge, and other organizations managing multi-million-dollar initiatives in renewable energy, electric grids, and electric mobility. As a co-founder and CEO of FlexiGrid, Alberto leads the development of next-generation technology to prepare power grids for the energy transition. Now, Alberto will be taking over controls, and he will be taking over the presentation from here. You're on mute, Alberto. I'm not certain if you're starting to speak yet.
Yeah, I was. Hi, everybody. Sorry for this. Yeah, and thanks for the introduction. I was very pleased to see the previous real project. I think my presentation will focus also to show some real example on the grounds of technologies that simply work. We just need to get them deployed. But it was lovely to see, you know, a 10 megawatt impact. You just install it, run it, and it works like expected. Why not? Why not do it? So yeah, I think yeah, I'm using more and more this motto that there's no Green Deal without a grid deal, and yeah, the grid, as we discussed before, you know, has become the largest bottleneck for the entire energy transition. Is already the largest cause of delays and cancellations of renewable energy projects, electrification projects, also the number one cause of curtailment and loss of renewable energy power that gets thrown to the garbage because the grid can take it. And yeah, and also cost and affordability. One thing I think we didn't mention before is that in energy transition is bringing energy prices down because of cheap renewables, but is sending grid costs through the roof. And one thing we have observed is that in most countries with advanced energy transitions, most of Northern Europe, we have come to a point where the number one component on the electricity bill is grid fees per kilowatt hour. So we pay more. I live in Stockholm, Sweden. 60% of my pre-tax electricity bill is grid. In Norway, 70%. And yeah, so there's a lot of discussions how to make energy production more efficient. Should we do wind or nuclear or renewables? But I don't think we discuss enough about grid economics and the immense impact on affordability. So, but it's starting. I see, I mean, I'm seeing a lot of change. I think we have a wonderful opportunity with the new commission. And it's great to see, for example, sorry, I made a mistake in the presentation. The gentleman above is not Christian Ruby, it's Dan Jorgensen, the Energy Commissioner of EU. And yeah, he says basically we need to double utilization of the grids and the connections we already have, right? It means rationalizing, digitalizing, and using AI in systems we already have. And then Christian Ruby below, which is the Secretary General for Eurelectric, you know, talking about, it's great to see this happened just the last month, these two things. We need to optimize existing infrastructure with grid enhancing technologies, with digitalization, with AI, with smart flexibility solutions. It's great to see. I think we didn't see this, at least I haven't seen this in the last year, such clarity, such good level of understanding of a complex matter like electricity grids by top leaders at EU level. Let me share with you, I call this the onion, okay? It's a bit complex, but bear with me. It's all gonna make sense to you. But at the core of the onion, you know, we have the core grid systems, okay? Then there are different layers of an onion, And in the last layer is the consumers, industrial or domestic consumers. And in between, some of the core grid systems and hardware and the end consumers, there are some layers of stack and markets, until we get to the outer layer. Then in the grid, we have transmission, we have regional distribution or mid voltage, and then we have local distribution or low voltage. Just today is about distribution, but sometimes I have to explain that 80% of the cost, 80% of the infrastructure, 80% of the CapEx and the OpEx of European grids is in distribution. And out of that, full 50% in low voltage. The other thing I want to bring to your attention is look at the average utilization of capacity, right? In transmission, we have 35 to 40%. When we go to mid voltage, it drops to 20, 25%. Once we go to low voltage, it drops below 8%, 10%, sorry. Last data we have for European average is 8% utilization of capacity. And well, in a sense, 80% of the capex goes to distribution because it's 3 or 4 times more capital intensive than transmission, because it's 3 to 4 times less efficient in the utilization of capacity as transmission. And so that's something that always fascinated me. And I think the next wave of innovation on distribution should attack that, because if we are able to increase these meters or double them, as Jorgensen wants to do, then we will reduce grid fees per kilowatt hour by 50% for end consumers. And again, this is in many European countries the largest component on the electricity bill for end consumer. So let's super quickly understand why there is this big gap in efficiency between transmission and distribution. One of the main reasons is if you look at the white part, there is a white part of the slide and orange, right? So let's look at the upper part. So TSOs, if you go to a control center of a TSO, they have real-time visibility of what happens in all their nodes. They have real-time analytics, so they can compute power flows and state estimation, voltage currents in every single section of the grid and upgrade in real time. And then they have real-time access to flexibility, typically hydropower plants or gas peakers, but also more and more they have also access to batteries, demand response, and other flex players. And so with these kind of superpowers, they can run the grid really efficiently. And these kind of control systems are provided by companies like Schneider, GE, Vernova, Hitachi Energy, Siemens. They are the traditional SCADA systems or in distribution ADMS. Then you have a next layer of markets. TSOs have certain power, flex power over spot price markets. It's called redispatch procedure, so they can even change some of the production program in the spot market if there are constraints. That's a flex superpower. And then they have entire flex markets, which are ancillary service markets, like frequency markets, and are nothing else than flexibility markets. Then on the other side, you have hydropower plants or gas peakers, but also more and more aggregators, battery operators, flex retailers like Tiber or Octopus, and virtual power plants, DERs, you name it, all the new kids on the block. And what you can see is that in the white part, in transmission, all the layers of the onion are beautifully connected. And there is a real-time interplay that allows the TSOs to run with a utilization of capacity as high as 40%. That's remarkable. Now, in distribution, some of these links are broken. If you go to a control center of a DSO, it's very, very different than the control center of a TSO. You don't see these superpowers interplaying in real time. And so, especially in low voltage, if you cannot see things on real time, if you cannot control stuff on real time, and if you have a security of supply mandate, the only option you're left with is to I mentioned the whole infrastructure for a peak that maybe happens 50 hours a year, plus a huge safety margin. This approach is called fit and forget. And then the rest of the year, you're floating in overcapacity. It sort of does the job, but it's immensely inefficient. And the cost of this approach is staggering. So, FlexiGrid, we have focused on fixing these missing links, What will it take to create the same real-time interplay between the inner part of the onion and the outer part of the onion so that we could have and what will be the impact, of course? If you were to equip the DSOs with these superpowers, there will be a convergence in efficiency from this 10% or less than 10% towards the 20 or 30 or 40% that you see in mid voltage and high voltage. And the beautiful thing is that everybody in the outer part of the layer of the onion is already ready to engage. The only reason they are not engaging is because the DSO doesn't have the tools to create this real-time orchestration. And that you can see very clearly in local flexibility markets like Nodes or Piccolo. They have very good liquidity in mid voltage with large consumers where the DSOs have some visibility, but they are really frustrated because they have no liquidity whatsoever in low voltage, where you actually have most of the flexibility. Most of the heat pumps, air cons, batteries, EVs are actually landing in low voltage. So yeah, there is a lot of people out there ready to engage but it takes two to tango. So we need to equip the DSOs with this new generation of innovation. This is what I call, just to summarize, the iceberg of flexibility. So far, the Flex ecosystem is just monetizing the tip of the iceberg, spot market and frequency service market. But most of the optimization potential is under the water, untapped, because the DSOs are missing the technology to do so. Well, here we have FlexiGrid. We designed FlexiGrid. This is a network of a section of the network of one of our customers in distribution. You can see the streets of a city right behind. So this is real low voltage. And you can see here the technology, compute real-time, power flows, identifying the bottlenecks, just like a TSO. And if you go to a distribution system operator, they can't do that. But here we're proving that the technology works. Here we are activating flexibility, and you can see we were able to wipe out most of the bottlenecks. There is a stubborn bottleneck there in the middle that will need an upgrade, but in this case, we were able to avoid 80% of the planned upgrades by engaging flexibility instead, huge savings. Here we have another project in New Zealand with one of the main grid operators there. You can see in this case, FlexiGrid is orchestrating on real time the charging of EVs so that there is never congestions or overloads. And this is an area where they couldn't connect more EVs because there was not enough capacity. But with this Flex orchestration, they could connect all EVs and get them charged before 6 a.m. every day and within existing infrastructure and without overloading any substation or feeders or lines. And last but not least, here I have a project with nodes using local flexibility markets. In this case, we're going to zoom in one of the substations in this network where you can see that in the morning we're fine, but in the evening, if we do nothing, we're going to have a huge overload in this substation. That's the upper curve, right? Light green or light blue. Below here, you have the flexibility available in the local flexibility market in this substation. And then if we take the dotted yellow line at the bottom is what happens if we activate all flexibility. Well, what we see is that we have more than enough flexibility to resolve the congestion. And then last but not least, you have this dotted blue line. I don't know if you can see the dotted blue line that goes right under the red line. That's the optimal activation strategy. We don't need to activate all flexibility, just enough to solve the congestion. And then we create an activation algorithm that activates on the market the cheapest combination, right? So this is the activation strategy basically that resolve the congestion at minimum cost for the DSO. And yeah, so yeah, sorry. And the last thing here with this I'm finished. You can see to the right or stack generating automatically the transactions and the activations of each and every agent that needs to be activated on the local flexibility market, just like it happens in transmission with the ancillary service markets. So yeah, the technology is here. That's my message, and it's TRL 10 because it's already running. We're working already with 25 DSOs. The key now is to scale it because it can create huge savings for end consumers, and it can solve curtailment, and it can reduce queues for new connections by a factor of 50% or more in most of these KPIs. So the problem is not the technology, but regulation. And let's be very frank and candid here. Most of the regulations around Europe and the world still remunerate the DSOs based on CapEx. And in most countries, also OpEx, but there's no profit on the OpEx. So basically this rewards blind expansion of balance sheet and the installation of more and more capacity at low efficiency. That's how they make profit today. And if a DSO today, most of our customers, if they use less CapEx and become more efficient, they get rewarded with a lower profit. That's like a punishment. It's a massive disincentive. So that's what it needs to change. You know, we need to remunerate DSOs so that they get rewarded when they are more efficient and punished where they are not. Today's regulation does exactly the opposite. And just the last 10 seconds, Iwan. Yeah. So this is already happening. Here we have some examples of regulations that are starting to create the right incentives and regulations to create the right economic signals for the DSOs to do the right thing, to do the cheapest thing, not the most expensive thing. Thank you, Iwan.
Brilliant. Thank you, Alberto. And I think the end of your presentation discussing regulation is a perfect segue into our final speaker. So we have Riccardo Vailati. Riccardo is currently leading the Quality and Innovation of Electricity Infrastructures team at the Italian Regulatory Authority, ARERA. The main activities are supervising electricity network investment planning and defining performance-based regulation. He has 15 years of experience in regulation of energy infrastructure, both at ARERA and at Acer. In 2001-2008, he was a power system consultant and researcher. He serves as co-convener of the Acer Electricity Infrastructure Task Force and as the chair of the Electricity Infrastructure Workstream at the Council of European Energy Regulators, CER. So a reminder, this is our last presentation before we enter the interactive Q&A session, but I would encourage any participants who have a pressing question for any of the previous speakers to use the chat function or make use of the chat function, and the speakers can then answer it directly. So Riccardo, the floor is yours.
Thank you very much. Thank you to CurrENT colleagues for the invitation to speak today. Let's go to the few slides that will accompany my considerations today. I will speak, you can go ahead with the next slide. I will speak shortly about mitigating the bias which favors capital expenditures over operational expenditures. And indeed, thank you very much, because it was a perfect assist from the previous intervention. We'll also speak about output-based regulation with an example of continuity of supply that is historically promoted network automation. And I will speak about a benefit-based regulatory scheme, which, however, is to some extent different than the proposal suggested by Acer and Florence School of Regulation. But let's go to the first topic with the next slide about reflections on the treatment of capital expenditures and operational expenditures. Indeed, there are a number of reasons to which network operators tend to favor CapEx. And an additional reason to those related to financial returns and stability is the possible presence of a hybrid approach like the one that was in place in Italy for 20 years, with rate of return regulation for capital expenditures and price cap regulations or incentive regulation for the operational expenditures. Here we started with the first measure, which intends to mitigate the capex bias. And from 2024, we applied the so-called fixed OPEX CAPEX share, FOX, as an acronym, more or less for the entire for the entire country, because the DSOs, the 19 DSOs to which this instrument applies, is more than 99% of the Italian customers. How this works? There is a predefined share of CAPEX, a fixed percentage, and a predefined complementary share of OPEX. And what is added to the regulatory asset base is the expenditure multiplied by the CAPEX share. So irrespective whether the network operator spends in something which is traditional CAPEX or something which is a traditional OPEX, the expenditure will be allocated based on these fixed parameters. This implies that the company will continue to maybe favoring CAPEX in the sense that it is less risky for intrinsic reasons, but there is no explicit disincentives to increase the level of OPEX and maybe reduce some CAPEX-oriented solutions. Well, there are a bit of details about the setting of the FOX, but in short, what we did to take into account the increase of grid investments was to set the FOX on the basis of historical OPEX CAPEX shares and forward-looking projections of CAPEX and OPEX over an overall 5-year period. But let's go to the next slide, as I'm seeing that the time is running. One example, a classical example of the so-called output-based regulation, focusing on outputs to network users, continuity of supply, which means interruptions, the number of interruptions over a year typically, the presence of very long interruptions. In Italy, the threshold is 8 hours, and also regulation and let's say dealing with resilience to extreme events. There has been a large bunch of instruments. The Italian regulator, the most relevant effect on the operation of DSOs was the increase of network automation at medium voltage level and recently self-healing automation as well. In the next slide, I don't go into the details, but in the next slide, I would only show the effect on the output, the interruptions. These are the interruptions without notice, and we had a significant improvement of performance, especially in the first year of the regulation. And then there was a kind of saturation. That's the reason why I did not even include the latest years, because they simply repeat the previous years. The new phenomenon, and it can be seen, for instance, in 2012 and 2015, is the number of so-called extreme events and the impact of these extreme events. There were years in which the extreme events related interruption were more than the interruptions deemed controllable and attributable to the responsibility of the DSO. And this brings to the last part of the presentation. If you can go to the next slide, please. which is benefit-based regulation. In Italy, benefit-based regulation is not the instrument suggested by Esser and Florence School of Regulation, which is in the end a kind of capex saving, so a cost sharing. What we did for the period since 2019 with an instrument limited to network resilience. And what we expanded from beginning 2024 is a regulation which is linked to the expected benefit of the new network intervention or a combination of CapEx and OpEx, of course, potentially. The requirement in short is that to get the additional rewards, the activity has to deliver more benefits than costs, according to the typical rules of the so-called cost-benefit analysis, which is an instrument used sometimes, not very frequently in distribution network development, but is an instrument used in infrastructure development planning. We had but maybe better. The scheme in the end is a pure rewarder, increasing the allowed revenues of the network operator. The reward is proportional to the project benefits, with the caveat that there is a cap, there is a limitation to a percentage of the project capex. There was an application in 2024, and the new application are scheduled by end of June this year. During 2024 and this year as well, we made a lot of discussion with DSOs, and one of the interesting outputs of this discussion is an updated list of the benefit categories, which were already defined some years ago, but now we have an updated list on which I will focus soon in the next slide, and approaches to calculate each benefit and to define the parameters. I would focus on this because I saw an interesting piece of the paper, of the CurrENT paper, discussing the benefits of new developments. And I had the impression that the list provided one of the last pages of the report is not far from what we introduced in our regulation. Expected reduction of customer interruptions during heat waves, during condition of extreme events, and during the rest of the condition, which we call ordinary. Expected avoided cost for the actions following interruptions, like, for instance, reduced use of emergency diesel generators and reduced post-fault intervention meant as OpEx, like vehicles to bringing the maintenance guys to intervene on the grids. As all avoided costs, we take into account both the direct economic costs and the saved emission of greenhouse gases of CO2. The expected reduction of interruption is also relevant for renewable plants, renewable power plants, and solar, wind, and so on. And also in the same field of continuity of supply and, let's say, voltage quality, one of the benefit categories is the reduction of severe voltage dips. Back to the concept of avoided cost, also the capex related to the extraordinary maintenance. Without a fault, there is no need to install a new piece of cable or other assets or other network elements. In the next slide, the second part of the benefit categories, also avoided continuous operation and maintenance cost, like avoided cutting of trees near the lines, near the overhead lines, avoided water consumption in water-cooled transformers. When it comes to interconnecting new areas to the grid, like, for instance, rural areas previously not electrified or islands, the benefit is in the reduction of the cost of electricity let's say, of energy consumption in general. Another benefit effect, which we decided to split into two sub-benefits, is the reduction in network losses. We decided to split here the emission effect and the direct economic cost, because the direct economic costs are already subject of a dedicated output-based regulation. And also, when increasing the voltage variation, especially in low voltage networks, there is an effect of a reduction of disconnection of renewable plants, especially solar panels. And last, there are two benefit categories, the last two, 12 and 13, regarding the reduction of congestion upwards, the so-called, sometimes called RES hosting capacity, when the congestion is from the lower level of the distribution to higher level of distribution or transmission grids, and the other reduction of congestion due to increased electrification, so the congestion due to electricity withdrawals, which in Italy we called loading capacity. Thank you very much for your attention, and any question is welcome.
Thank you very much, Ricardo. And as I mentioned previously, this is now the Q&A with participants. So I would encourage all participants or any participants with a question to use the chat function or the function in Teams to raise your hand, where we'll be going on a first come, first serve basis for the questions. And maybe to get things started, I'll then, on the topic of regulation, I'll pose a question to the two representatives from IPTO. Within the existing regulatory framework and background of Greece, do you think the benefit sharing model just discussed by Ricardo could be used successfully to promote the deployment of innovation in Greece, or would there need to be other systemic regulatory changes? Please provide why or why not, in your opinion.
If I can give some considerations on
Please.
that. Regulators do not be offended like to technologies. Regulators are keen of a concept which is called technology neutrality, and we still believe that when you put in place a specific instrument, a reward, for instance, the companies have a direct push to look for something new. But excluding the case of pilot projects, which, well, of course, it's a possibility. The pilot regulatory incentives at the very beginning to understand if a technology is plausible, but this is not a big this is not a big effect, and maybe, as also mentioned in one of the previous presentations, it can even have the drawback of postponing the deployment, because it takes too much time to look on the pilot project. It's better to attempt with an overall regulation which favors maybe deployment on a limited scale on some reduced areas, but start immediately from the field. This is our approach in the recent years. Of course, it's not always a success. With advanced automation, self-healing automation, and so on, we have seen mixed results. Overall, an improvement of continuity, but not as expected, not as important as expected. So it's well, when it comes to innovation, I believe that many years ago someone told me that there are three possibilities: normal, extraordinary success, or significant failure, and that's, I believe, continue to be it will be forever the result of innovation. The good thing, I believe, in this benefit-based regulation is that We are, of course, with the caveat that some parameters may be a bit uncertain, the impacts over 25 years, which are typically counted for this exercise, will be uncertain. But if you tune properly the sharing of what is given to the customers and what is given to the network operators as a reward, regulators are comfortable not to, let's say, over remunerate too much the network operators. The most of the benefits will always go to the consumers because these technologies, the various type of innovative or traditional technologies, will go to the benefit of end customers. And another important effect is that the effort that we have seen in Italy to better understand the grids, to identify the metrics, is an effort which helps the DSOs in better knowing and planning their grids. So we have a significant effort in the topic of distribution network development plans, and this is, let's say, correlated to the benefit-based incentive because the DSOs are a bit rethinking their approach to the networks, considering to move away from the fit and forget and the potential oversizing linked to the fit and forget approaches, and better understand how the grid, let's say 5 year ahead or 10 year ahead, will actually operate.
Alberto, I see you have your hand raised.
Yes. Because I cannot see questions on the Q&A section, right? Should I write it or should I ask it?
Ask it directly, please.
Yeah, that's okay. So one thing that I love to see this approach that the method that you propose first guarantees that there is system savings, right? Otherwise, if you just do TOTEX, there is a risk that DSOs spend a lot of money in OPEX or software or whatever, but that's not a guarantee that it will bring down grid costs for end consumers, which is the key, right? So I think that's a great provision. Otherwise, spending in digitalization doesn't mean cost reductions, unless the regulator puts the foot down and say, I'm not going to approve anything that won't, unless it will reduce costs for end consumers, right? So that I like very much. One question that, and this is something that we see between DSOs, is that they look at the profit. So this is EBITDA of option A cables, and if I do, this is the EBITDA of option B, an alternative, right? More efficient alternative. So if the profit I make in option B is less, they conclude I'm disincentivized by the regulator to take option B. We follow regulatory signals. And so, yeah, this is more of an opportunity cost pricing, right? So that the policy is done to ensure that in the option B, you make the same profit, no more, no less, Also still contingent that there is a reduction of cost for end consumers. And I think that well, my question to you is, what do you think about that approach, right? Because sometimes I think it addresses better system cost in the sense that if the option B doesn't leave the same profit and they go for option A, they are increasing system cost. They are taking the more expensive solution just because it gives them more profit. So I think regulation should be addressing that the expensive solution should not end up in more profit, because otherwise you will have people trying to, profit maximization is the mandate of the CEO of a stock listed company, and you can call it immoral or something, but it's legal and is what the shareholders expect. So in that kind of profit maximization exercise, I think regulation should ensure that, you make the same profit, or at least not less profit, when you do the option that results in lower cost for consumers and lower system cost.
Thank you. If I can give a couple of considerations,
Sure.
thank you very much for this comment. Indeed, when I mentioned mitigating the capex bias, the capex bias will continue to exist precisely due to the reason that you mentioned, because it leads to turnover. Let me use a couple of terms. Turnover, which is something that the company wants to maximize. It's reasonable, it's their expected behavior, but also returns. Returns is what can be changed by the regulation, because when you put a rewarder on a small project, the return on that project maybe will be, just to give an example, it will become 7% instead of the standard 5%. And the companies, it's true, it's certainly true, they focus on turnover and profit maximization, but also maximization of returns is very important for the company in deciding on the investment.
Yeah,
when you have an investment that goes, let's say, 200 basis points above because of the rewarders, well, maybe the small project will succeed because, well, the company has mixed feelings and may be under shortage of funds. So it's not always easy to always put maximizing the expenditures to maximizing the turnover, but also less expensive projects leading to higher returns thanks to the rewarders may be appealing to the CEO, which of course reasonably will pursue the profit, the financial maximization. But it's not only profits, it's also returns. And this is the lever via which we try to change the net behavior of the operators.
But I
Thank
mean,
you.
I work at an operator, just super quick. I've been in executive committee in Vattenfall, you know, with a large grid, and I saw sometimes leaving on the table the small project with high return for the bigger, much bigger project that leaves more EBITDA. That's why I put the question, because there's 200 basis points more return didn't result in a change decision to do the right thing. So yeah, and if you look at the analysts, right, especially the stock listed companies, the analysts look at EBITDA. You know, so analysts put pressure on the CEO to maximize EBITDA. If it is a lot of turnover expansion, but with poor EBITDA or losses, then the stock will suffer, and so that's why I think maybe EBITDA, Mark, just to say it will leave the same EBITDA per kilowatt as the other alternative. Then I think in the executive committee, then it will remove the reason not to do the right thing, so to say. Yeah. But
thank you, Alberto.
sorry.
I see Konstantinos has his hand raised, and then there is a question in the chat which I would like to pose to all speakers. So, Konstantinos.
Yes, just to add a comment. So I work in the R&D, so regulation is out of my expertise, and this is a very complicated subject. Sometimes we try to solve a problem and create another one. I just want to comment about the research pilots, and I'll give 3 examples. For example, the one was the MPFC that now IPTO is considering in using another location. We had also another project, dynamic line rating, through a research project, which was very successful. And now IPTO is funding its own DLR project to further examine these technologies. And another example were the PMUs. We had initially 2 PMUs. Through different research projects, there are now 20 PMUs. There are initially some algorithms being developed through research programs, and now IPTO is in-house developing its own algorithms based on PMUs. So what I want to say, sometimes research projects help things starting to move and yes, accelerate innovation.
Thank you, Konstantinos. So as I said, there is now a question from the Q&A function of the chat. Do you think that a policy that proposes the share of open data regarding distribution network infrastructure and connected users can be useful to foster the planning of the system and the integration of innovative solutions? If there are any speakers who would like to integrate, so Mark, I see your hand raised.
Thanks, Ewan. Yeah, in short, yes, I do. I think that the sharing of data on the distribution network would allow assistance, if nothing else, for decision makers, whether it be the DSOs or others. We would be able to look at innovative grid technologies. A lot of the people who are supplying them have the ability to quickly take up and assess the beneficial effects of them. We can share that information then to the decision makers. And I already mentioned earlier, I mean, a lot of the DSOs are hard pressed to do the evaluation work and the time and the energy that's required to do that. So it would be, I think, supportive to be able to provide them with interesting results, the scale and cost of actually putting some of these innovations on for them to quickly consider and either adopt or at least provide feedback as to why those solutions wouldn't be beneficial for those particular applications. So yeah, sharing data would be great. And I think it's starting to happen. But obviously a more transparent and open platform would be welcome and beneficial.
Thanks, Mark. And again, I would encourage any other questions you have. You can either use the chat function or you can raise your hand and we'll look to take it through there. Maybe I have a question now for Rina. So the recent IEA reports have looked at the rise of congestion and curtailment, where insufficient grid access and inadequate grid connections mean we're not making the most out of the renewable energy sources available. At the end of your presentation, you listed 5 key steps that we can use to promote innovation and integrate these renewables. Which of these would you say is the key factor? You mentioned benefit sharing. Is it regulation? Is it appetite? What for you is the most important?
Thanks for the question. So out of the 5 recommendations, which one is most important for resolving congestion issues?
Yes.
Is that your question? Yeah, okay.
Yes.
Great, thanks. Yeah, so recently we published indeed a commentary focusing on congestion management issue. It came to light because of the in-depth review we did for the Netherlands. And yeah, in my presentation, the Netherlands wasn't shown, but if you look at the commentary, you can see that actually the situation is quite dire there in terms of the grid being in a literal gridlock, so to say, that everything is apparently occupied in terms of connecting any new generation, but also demand units. So what we have noticed, though, that congestion is more perhaps a costly problem at transmission level than it is at distribution at the moment. And there are a number of reasons for that. Some of the feed and forget sort of approach that you mentioned is a reason why congestion may not be visible today in distribution grid. And if it becomes visible, then it really becomes a quite big problem, because that means you have reverse power flows in the distribution grids, which then have an impact on the substations and so on. So there, it's a concern then mainly for transmission grids. And then coming to your point about which of the 5 recommendations, of course, regulation has a role to play. And I'm glad to have ARERA on board this conversation today, because they are one of the pioneers in terms of developing regulation that is encouraging transmission system operators to adopt technologies like dynamic land rating to decongest the transmission grid. Also, good examples from Belgium could be mentioned. But also what's important is the planning aspect. And here, really, the transmission system operators should be on the way, if not already, identifying where the suitable locations for unblocking with the grid enhancing technologies in the transmission grid, more on a systematic like approach. And because you don't need to equip every single transmission line with a grid enhancing technology, you can focus that on specific bottlenecks within the system to really leverage and unlock the maximum benefit. So really a system-wide study should be done, and then planning the deployment really at wide scale. And that's where the regulator should support the TSO in deploying that at large scale. So those 2 key aspects.
It all starts with planning, right? I love that approach. I think, and planners don't have today the tools They have great tools to plan for transformers and substations. They don't have the right tools to plan for what I call hybrid grid, which is a combination of cables, transformers, combined with, modular power flow or dynamic rating or some form of batteries, or a combination of all of these. And also the regulators don't have the tools to do this planning. So I think you put the finger on the right spot there.
Thank you, Alberto. And I realize now that we are running close to time and we're coming to the end of the webinar. So unless there are any last minute interventions, I will pass the floor over to Mark Norton, who will give the concluding remarks of this webinar.
Thanks, Ewan. I can't see anybody jumping in, so maybe I'll take the opportunity and just say, well, first of all, great thanks to your time, the people who've joined this call and the inputs you provided, and particularly, obviously, the presenters. Thank you very much for your time and effort, and I think for what was a very interesting and profitable discussion. What we heard today, I think, and if I try to summarize, is that there are significant common issues and messages that are coming from all of the presenters. We've got a major challenge that are coming down in network development, 2 times the growth that we're doing currently at the moment that we need to manage going forward. Significant network delays that have been actually seen. There's challenges in the workforce and the people who are going to be able to address, manage, and find solutions to keep the network developing at the rate and pace that we need, and also the materials in order to support that. As a consequence, one of the things that we must do is maximize the grid, and that's an absolute must. I think we heard that across the board, both from the presenters but also the audience. And that we've heard from presenters some of the tools and techniques that have been tried, whether they be owners, developers, or regulators, in order to maximize the existing grid using innovative grid technologies, how they've managed the risk and offset the project risk against that of the system and the benefit to the system, and how that's been valued, effectively the art of the possible. And we've seen that IGTs or innovative grid technologies can do this. They can provide the benefits, and those benefits from various different metrics that I took note of are huge. 350 billion saving by 2040 on the distribution network is an enormous sum of money. And if you look at it in another way, which is the ability to deliver, the portfolio of projects much more quickly, 4 to 7 years saving in the present environment is probably, equally as impressive as the numbers in the form of euros, and probably more essential going forward. And I've also taken great heart that not only have we seen that technologically solutions are out there, but also the support structures, the regulatory structures, the pipeline, the workforce issues can be addressed. So I think after a great discussion, a lot of the learning from this can actually be put into action. And I just conclude by saying thanks for your time, thanks for your efforts. And I look forward to working with a lot of you to try and action some of these thoughts and ideas going forward. So thank you all.
Thank you.
Thanks very much, Mark. So just a reminder from CurrENT side, we'll be uploading the recording of this webinar as well as the key takeaways and summaries on our website, and we'll send a follow-up email to all the participants in case there's any information you missed. And if you'd like to cooperate with CurrENT or any of the speakers here, please don't hesitate to reach out, and we'll look to facilitate that where possible. So thank you very much, and wishing you an enjoyable weekend or rest of the day.
Thank you. Bye.
Thank you.
Thank you.
Thank you. Bye-bye.